Internet videos often portray these carnivorous plants as bloodthirsty predators with snapping jaws straight out of a horror movie. The biological reality is slower. These organisms evolved unique adaptations to survive in bogs where the soil lacks basic nutrients. Buying one of these plants means you are committing to manage a specific biological trapping mechanism that functions on its own schedule. Successful cultivation requires looking past the visual spectacle and matching the plant's specific needs to the actual maintenance routine you can provide. We can evaluate your options using a framework we'll call the Carnivorous investment. Before buying, we need to check 3 distinct criteria. First is aesthetic novelty. This measures the visual appeal of the plant and whether it features interactive, moving parts. Second is pest control efficacy. This is the practical math on the volume of insects the plant will eliminate from your environment. Third is maintenance tolerance. These plants demand strict inputs, usually mineral-free distilled water or forced winter dormancy. This quadrant chart maps out a central biological trade-off. The x-axis tracks the trap mechanism, moving from passive to active. The y-axis tracks catch efficiency. Dramatic, kinetic movement usually results in low catch volume, while passive systems offer high efficiency. We are going to put 5 distinct biological trapping methods head-to-head on this graph to see where they land on the spectrum of effort versus impact. We start on the active end with the Venus Flytrap and its kinetic snap trap. Keeping one alive requires rigorous inputs. You must use 0 mineral distilled water and provide a cold winter dormancy period every year. That maintenance buys you a visible mechanical snap, but executing that movement costs the plant an immense amount of energy. A single trap often dies off after closing just 3 or 4 times, making it unsuitable for high-volume pest control. On our matrix, the fly trap logs in as an active trap requiring high maintenance with low practical utility. Next is the cobra lily, which uses a complex maze trap. The input demands here are specialized. Its root system evolved in cold mountain springs, so you have to water the soil with chilled or iced water to keep the plant from overheating. This diagram shows how it captures prey. The plant manipulates light using translucent false exits. The insect flies toward the fake windows until it exhausts itself and drops into the pitcher. You get striking aesthetics, but if you fail to keep the roots cool, the plant will collapse almost overnight. Both the snap and maze traps function as high-maintenance projects for dedicated collectors. They sacrifice practical utility to deliver a specific visual spectacle. Shifting focus, we look at passive systems, starting with the Sundews adhesive trap. The primary requirement here is consistently high ambient humidity, which the plant needs to produce its sticky mucilage. Once the humidity is dialed in, the Sundew operates as an always-on biological flypaper. It captures dozens of insects without expending energy on movement. This is effective at clearing micropests like fungus gnats from a room, though the plant eventually coats itself in a messy layer of dead bugs. Updating the matrix, the Sundew scores as a passive trap with medium maintenance and high utility for micropests. In a larger scale, we have the pitcher plant and its pitfall trap mechanism. These require vertical growing space for their tall tubes, along with hours of bright light. The trap uses nectar to lure prey to the rim. Bugs slip and fall into a deep stomach pool, allowing the plant to process massive catch volumes. This provides high-volume pest removal on an outdoor patio, but it lacks any interactive movement. Adhesive and pitfall traps are a pragmatic investment. You give up the cinematic snapping action, but you gain relentless pest-clearing volume with less daily fuss. Finally, we hit the extreme endpoint of biological efficiency, the bladderwort, which uses a suction trap. It requires a fully aquatic tank or a thoroughly waterlogged bog setup to survive. The mechanism relies on hydrostatic pressure. The plant pumps water out of tiny bladders to create a loaded vacuum. When a trigger hair is brushed, the trap door opens, vacuuming in the prey in a fraction of a millisecond. It is the fastest capture movement in the plant kingdom. Because these traps are microscopic and live underwater or in the soil, you get no visual spectacle at all during the process. The bladderwort separates efficiency from aesthetics. It is an investment reserved for builders of specialized terrariums and aquatic ecosystems. To make the right choice, look at this decision tree. It starts with one question. What is your primary goal? If your goal is pest control, the path splits based on the target. For gnats and mosquitoes, go with the Sundew. For large flies and wasps, choose the pitcher plant. Home gardeners should follow this passive pathway for low-fuss results. If you want a novelty display, the path leads to the Venus Flytrap and the cobra lily. Choosing this path means committing to strict environmental controls and winter dormancy management. And if you are building a specialized ecosystem, that leads directly to the bladderwort. Aligning your lifestyle with the correct biological mechanism is the only way to prevent dead plants and wasted effort. Invest in the plant that matches your daily maintenance tolerance, rather than the one that looks the most dramatic on a screen.